So our theme continues to be intermolecular forces. Here we're going to take a look at identifying intermolecular forces in compounds to determine how that impacts solution formation. So the key to predicting if a solution will form or determine why a solution will form is to begin by identifying what type of compound you're dealing with. Is it ionic or molecular? Ionic compounds can only interact with other substances through ion dipole forces. So it has to be mixed with a polar molecule. Now, if something is molecular, then you need to determine, is it polar or nonpolar? Nonpolar molecules can only interact through dispersion forces. Polar molecules have dispersion, but interact primarily through dipole-dipole forces or hydrogen bonding if available. So here we've got this image that just kind of reviews the intermolecular forces we've been talking about. So dispersion, remember again, that's that random movement of electrons. Dipole-dipole, that's between our polar molecules. So we've got examples of acetone and chloroform. Hydrogen bonding, that's that interaction of lone pairs on oxygens, nitrogens, or fluorines with hydrogens bonded to nitrogen, oxygen, or fluorine. So we say that here with ethanol and water. And then ion dipole, that's our polar molecules interacting with charges. So something like a sodium cation. Now, once our available forces are identified, if the solute and the solvent share similar strength forces, then a solution is likely to form. We often say that nonpolar solvents dissolve nonpolar solutes. This is because they share dispersion forces of the same strengths, while polar solutes dissolve in polar solvents because of the dipole-dipole or hydrogen bonding interaction. Nonpolar molecules do not dissolve in polar molecules because their weak dispersion forces are not strong enough to break the stronger solvent-solvent interactions required for mixing. Now, some molecules have mixed or intermediate polarities. This tends to occur in compounds that consist of chains that contain an oxygen or nitrogen typically. They have a nonpolar region that can interact with nonpolar molecules, while they also have a polar region that can interact with polar molecules. Solubility in polar solvents decreases as the size of the nonpolar region increases. So we'll get some examples of identifying our intermolecular forces and seeing what force is going to be responsible for the formation of our solution. So with the materials we're given a solute and a solvent, and we are assuming that the solution forms. And we're looking at the intermolecular forces to determine why. So again, we've got to start with identifying what type of compound we're dealing with. Is it ionic or molecular? So if I look at I2, there's no metal present. It's only iodine, which is nonmetals, so it is molecular. My solvent, C6H14, is all carbons and hydrogens. Those are all nonmetals, so that is molecular. So then we determine, is the molecule polar or nonpolar? So looking at I2, my bond is between the same atoms. It's a nonpolar bond. I only have one bond in that molecule. It's nonpolar, so I2 is a nonpolar molecule. My C6H14. So remember C6H14 from our previous chapter, that's hexane. It's 6 carbons, all single bonds, that's hexane. That hexane's got carbon-carbon bonds, which are nonpolar. And it's got carbon-hydrogen bonds, which are nonpolar. It has all nonpolar bonds, so it is a nonpolar molecule. So we identify our forces. So if I've got I2, I've got my iodine. Iodine can interact with other iodine molecules through dispersion forces. Those are the only forces available to our nonpolar molecule. So that's my solute-solute force. It's what holds iodine to other iodine molecules. And then my hexane. So hexane is naturally a liquid. It's going to be in that liquid state due to its intermolecular forces. It's nonpolar, so those intermolecular forces are dispersion forces. So we're looking to see what causes these to mix. We're looking to see what forces these compounds have in common. So the strongest force that they have in common that's going to allow them to mix will be the dispersion force. So dispersion will be the solvent-solute interaction. So the iodine and the hexane are going to be able to mix and form a solution because they share those similar strength dispersion forces. So now we'll look at some slightly more complex molecules. So I've got this C6H5NH2 molecule, and it's being dissolved in CH2Cl2. These are both organic compounds. They contain only nonmetals. Since they contain only nonmetals, both of these are molecular compounds. So then we need to determine if the molecule is polar or nonpolar. Now, when I look at my C6H5NH2, I've got this group here that's all carbons and hydrogens. Those are all nonpolar bonds. But I have this NH2 grouping here. So remember that from our previous, it is an amine. So remember, NHs or nitrogens are amine groups. So that amine here, it's got nitrogen-hydrogen bonds, which are polar. And it's got a bond between nitrogen and carbon, which is polar. So that region is going to have these polar bonds, all of which are going to be pointing towards that nitrogen with the lone pair. So we have a polar region. This particular molecule actually has one of those mixed or intermediate polarities. So it actually has both polar and nonpolar regions. Now, because it has that polar region, we can describe it as having some polarity. So it's got some polar, but it also has some nonpolar. Now, if I look at my solvent, I've got these carbon-chlorine bonds, which are polar. Chlorine is more electronegative, so the electrons are being pulled towards the chlorines, and it's unsymmetrical. So this is a polar molecule. So when we identify our forces, what's holding the C6H5NH2 in its particular state is going to be dispersion, because we find dispersion in all substances. And it's got that polar region, so we're also going to have dipole-dipole. And if we've identified our substance as being polar, the other thing we take a look at is, can it hydrogen bond? So I've got those criteria. I've got nitrogen, hydrogen, and I've got that lone pair. So we have hydrogen bonding. So that's what's going to be allowing C6H5NH2 to attract to other C6H5NH2 molecules. So now we do the same thing with our solvent. We look to see what our solvent has. It's a polar molecule, so it's going to have dispersion. And it's going to have dipole-dipole. So again, we look to see if it can undergo hydrogen bonding. I have hydrogens here, but they're attached to carbon. Hydrogens attached to carbon do not hydrogen bond. So that molecule only has dispersion and dipole-dipole. And that's what's going to cause that CH2Cl2 to bond or mix or attach to other CH2Cl2 molecules. Now again, these do form a solution. So we're looking to see what their like forces are. What forces do they have in common? The strongest force that they have in common is the dipole-dipole force. So these two are going to mix through dipole-dipole interactions. So that will be my solute-solvent interaction. So again, we are looking for the strongest force that these two substances have in common that would allow them to mix. Now our next one, we're looking at CH3, CH2OH. So again, remembering back from our previous chapter, I have an organic compound here, got an OH, we're looking at an alcohol here, being dissolved in water. Again, both of these compounds contain only nonmetals, so they are both molecular. My solute, if I'm looking at my polarity, I have this portion with carbon-carbon and carbon-hydrogen bonds. So this area is non-polar. And then I've got this OH. I've got oxygen-hydrogen bonds, which are polar. I've got lone pairs, which make it unsymmetrical. So that region is polar. So again, we're going to have a mixed polarity here. Mixed polarity is going to be common when we have more than one center atom. But if I look at my water molecule, I have a simple atom, a single center atom. The oxygen-hydrogen bonds are polar. The lone pairs make it unsymmetrical. So the water is a polar molecule. So when we look and see what intermolecular forces we have, solute-wise, it is dispersion. Because of that polar region, we can have dipole-dipole. And then I have the oxygen-hydrogen bond with the lone pair. So we have hydrogen bonding. Then looking at my solvent, again we have dispersion because dispersion is found in all substances. My molecule is polar, so it has dipole-dipole. And then we have hydrogen bonding. Again, I have the oxygen-hydrogen bond, and I have lone pairs. So, my alcohol here, this is an ethanol. Ethanol is a liquid. It's a liquid because it can interact through these dispersion, dipole-dipole, and hydrogen bonding with other alcohol molecules. Water is a liquid because it's going to interact with other water molecules through dispersion, dipole-dipole, and hydrogen bonding forces. Now, when the alcohol dissolves in the water, the force they share, the strongest force they share in common, is hydrogen bonding. So the ethanol dissolves in water due to hydrogen bonding. That is our solute-solvent interaction. So we've looked at going through and identifying what intermolecular forces we have and seeing what forces our compounds share in common to determine why they would mix. But we also want to use that information to determine which molecule might be more soluble in a particular solvent, or what solvent might be better to dissolve particular solutes. So if we look at problem number 4 here, we're asked which of the following molecules would we expect to be more soluble in water, a CCl4 or a CH2Cl2? So we're going to break this down similar to what we did with the previous problems. We're going to look at the solvent, my water, and my possible solutes. So if we look at the water, we've already described the water as being polar. So it has dispersion, it has dipole-dipole, and it has hydrogen bonding. So that's my solvent. If we look at our potential solutes, if I have a CCl4. So we could draw that out. We've got carbon with single bonds to 4 chlorines. All of carbon's 4 bonds are chlorines, which means it's going to be symmetrical. All the corners are the same. So that's going to make that molecule nonpolar. So as a nonpolar molecule, its intermolecular forces are dispersion only. But if I look at CH2Cl2, again, we could draw that out. I've got my carbon in the center. 2 of my corners of my tetrahedrons are hydrogens. 2 corners are chlorines. It's unsymmetrical. The minute it's unsymmetrical, it's polar. So being polar, we have dispersion. We have dipole-dipole. There's only hydrogens bonded to carbon, so there's no hydrogen bonding. So we've got dipole-dipole. So when we're determining which solute is likely to be more soluble in this solvent, and this is a polar solvent, we're going to look for the molecule that has the more common forces, the forces that are more alike. So water being polar has more similar forces to the CH2Cl2. And that common force is going to be the dipole force. So dipole, dipole. Even though water can hydrogen bond, it's a very small molecule. The dipole-dipole is going to be strong enough of an attraction that it will dissolve the CH2Cl2 in the water. Now looking at problem number 5, we're asked which solvent would CH3CH3 be more likely to dissolve in, hexane or water. So we're doing the same thing. So this time CH3CH3 is going to be the solute. Looking at that particular formula, there's only carbons and hydrogens, which makes this a nonpolar molecule. So as a nonpolar molecule, its only intermolecular forces are dispersion. Now if we compare that to our potential solvents, we have a C6H14 versus water. The C6H14 is nonpolar. It's only carbons and hydrogens. So it has dispersion. Water is polar. Remember, water has dispersion, dipole-dipole, and hydrogen bonding. So when we're comparing our forces, even though water has dispersion, it has the stronger dipole-dipole and hydrogen bonding, which means that the solute, which is nonpolar, its strongest force is dispersion. Dispersion typically is not going to be strong enough to break the dipole or hydrogen bonding found in the water, but it can interact with the C6H14. So my C6H14 is going to be the solvent that solute's more likely to dissolve in because they share those like dispersion forces. Now, I just said that typically dispersion forces are too weak, but there are exceptions, and we see some of these exceptions when we have this mixed polarity. So we can look, for example, at pentyl alcohol. So we've got this long chain, so pent, 5. The alcohol, we've got that OH group. Now we're told that it completely mixes with octane, C8H18. But methyl alcohol is insoluble in octane, and we're asked to explain why. So we're looking at 2 alcohols. The difference is their numbers of carbons. So in both cases, we have this nonpolar region. while at the same time having this polar region. So both molecules have mixed polarity. We're told that one dissolves in octane and one does not. Now, if we look at that octane, it's only carbons and hydrogens. This is a nonpolar molecule. So the octane has only dispersion forces. But that octane's a long molecule. So remember with dispersion forces, as our size increases, the strength of the dispersion increases. If I have a long chain of 8 carbons, it can stack very well with other long chains of 8 carbons. So we're going to have fairly strong dispersion forces. So we've got that long chain with the large surface area. Now, if we compare this, we look at our pentyl alcohol and our methyl alcohol. We're told that the methyl alcohol does not mix with the octane. If we look at that nonpolar region is small. It has very weak dispersion. Its stronger forces here are going to be coming from the dipole-dipole and hydrogen bonding. So in that case, the methyl alcohol, its dispersion forces are too weak to interact with or break the dispersion forces of the octane. So remember, we've got to break octane's attraction to other octanes in order to mix. But the pentyl alcohol has this large nonpolar region. That large nonpolar region is going to have strong dispersion forces. Even though it has this polar region, it's going to be weak compared to the long dispersion. As a result, that long nonpolar region with the strong dispersion forces, it's going to actually be able to stack very nicely with large surface area against that CH18 and have strong attractions. So the pentyl alcohol is going to mix because it's got that strong dispersion forces similar to the octane, whereas the methyl alcohol, its dispersion forces are weak, so it doesn't share similar strengths. So we have to have similar strength forces in order for our compounds to mix. So we've talked a lot about intermolecular forces in this chapter. We looked at them in relation to boiling points, melting points, phases, and now solution formation, so the solubility of a compound. We're going to continue to look at a couple of properties of solutions, which will finish up our discussion here with intermolecular forces. Now, one last thing we want to touch on with that intermediate polarity real quick is that molecules with intermediate or mixed or competing polarities have both polar and nonpolar regions. So we've mentioned that already. Now, the nonpolar regions are considered to be hydrophobic. So we'll see that term used often, hydrophobic, often water-fearing, because they don't mix well with polar substances. So that would have been what we saw in our last example. We have that large nonpolar region. It doesn't interact very well with polar substances. While polar regions are considered to be hydrophilic or water-loving, overall solubility is governed by the ability of the attractions to offset one another. So again, that's what we saw in our last example.